Welcome. My name is Knut Hinkelmann. I'm from FHNW, University of Applied Sciences and Arts in northwestern Switzerland. The objective of this presentation is to show how you can build AI systems by combining two ways of reasoning: data-driven machine learning and knowledge-based systems. Marvin Minsky once said, "The brain happens to be a meat machine." This can be regarded as a metaphor for artificial intelligence. If the brain is a machine, can we achieve human-like intelligent behavior also with a different kind of machine, like a computer? Or even more, can a proper understanding of the meat machine help us in building artificial intelligence? This is the objective of this presentation. I will show that the analogy to the brain can guide us in building artificial intelligence. And let us first have a look at what is human thinking. The brain can be regarded as first a kind of supercomputer that can process massive amounts of information. With our senses, we simultaneously receive information which we filter, combine, and which we react upon. On the other hand, we can regard humans as rational thinkers. And rational thinking means for our behavior, we can provide arguments for our decisions, for example. And there's a close relation between rationality and logic, which allows us to model rational thinking. A similar distinction is made by Daniel Kahneman, who distinguishes between two modes of thinking. System 1 is fast, instinctive, and emotional, while System 2 is slower, more deliberative, and more logical. Thus, one can roughly compare System 1 to the processing of massive amounts of information, and System 2 corresponds to the rational thinking. So with this in mind, we now have a closer look at the history of artificial intelligence. The founding of artificial intelligence is usually associated with a workshop at Dartmouth College in summer 1956. This workshop was initiated by John McCarthy, who also picked the name artificial intelligence. 11 researchers met there for several weeks. After that, there was the first phase of artificial intelligence, so understanding the basic principles. This first phase is mainly dealing with rationality. And this phase was based on a hypothesis which is called the physical symbol system hypothesis. It means that thinking is a kind of symbol manipulation. And what are the symbols? Symbols are, for example, words. When we talk about natural language, we have symbols, which are the words which we express. But there are more than words, there are also concepts, ideas behind that. We can have symbols for these concepts. And then we can do logical thinking. So we need some kind of rules or reasoning for that. This was the first phase, and researchers try to understand thinking based on this physical symbol system hypothesis. And after the understanding of these basic principles, there was the first type of artificial intelligence. This was in the 80s. And one keyword for that is expert systems. So researchers were able to build expert systems, and they were already used by companies. So what is an expert system? An expert system consists of a knowledge base. The knowledge of the human is put into the knowledge base. This is what is called also knowledge engineering. And then there's an inference engine that can process this knowledge. And now non-expert users can query this expert system, and they can get answers or advice for problem solving. So in this case here, the physicians are the experts, and also non-experts now can use the knowledge of the experts in that area. Okay, what is behind that? Yes, we have the human knowledge. On the other hand side, we have the systems. If we want to automate that knowledge, for this we use a knowledge base. The knowledge engineering is creating this knowledge base. So the humans create a knowledge base of their knowledge. And as I said, there were practical applications, quite successful practical applications of that. But nevertheless, the interest in AI dropped. What was the reason for that? Why did the interest drop, and why weren't there that many applications and usages of that? Now we can look at something different. The idea was to build a rational system with rational thinking. And here's a quote that I found about self-driving cars. It is hard to imagine discovering the set of rules that can replicate the driver's behavior. This was in 2006, not even 15 years back. So it is difficult to find the rules for driving a car. So how do we recognize an obstacle? How hard do we brake, or how much do we turn the wheel to get out of the way of an obstacle and so on? It's difficult to express this, but we are able to do that. Another example, face recognition. It is easy for us to recognize people. If I see a person again, I'm aware that I met this person. Often I also have the name for that person. But this is not easy for our system. We cannot easily derive and describe the rules for a system to recognize a face. What distinguishes one face from another face? And we see this. If there is a newborn, we have the discussion. Is it more like the father? Does it look more like the mother? And we have different opinions, and we cannot really say why it is. We try to do something, the same nose, the same ears, but we cannot really describe it. And now we have approaches to deal also with that. And this is now the second hype of artificial intelligence, using statistical machine learning to deal with this huge amount of information and process it without having explicit symbols for it. So what is behind that? We already said that we have the human knowledge and we have the automated knowledge, but now we can distinguish two kinds of human knowledge. On the one hand side, we have this knowledge that we are aware of, that we can use to build a knowledge base. On the other hand side, we have this what we call also the tacit knowledge, the knowledge that we are not aware of. And now the question is, how can we build an automated knowledge for this tacit knowledge? And this is now where machine learning comes into the game. As we are not aware of the tacit knowledge, we cannot engineer it. We cannot build a knowledge base of it. But if we have data, then we can learn from that data and learn the knowledge and use it in a system. And we can automate it. Not directly from the human, but indirectly from the data. So the data would have information, for example, about faces, text recognition, text translation, images. So we have different kinds of data that we can process, where we use this amount of knowledge processing that we have now with new machines to deal with it. Keyword behind this is also deep learning. Neural networks with several layers that allow us to process this huge amount of information that we have in images and so on. And there are a lot of interesting applications for these deep learners. One information that I already mentioned is the recognition of obstacles, what we use for self-driving cars. On the other hand, we also have this face recognition. Recognizing faces, we use it, for example, to provide access to our mobile phones. Another very relevant application is diagnosis of diseases. In this example, cancer diagnosis. So we have a lot of images where we also have cancer on it, and now the system learns the characteristics so that it is possible to identify whether a person has cancer or not. Also with text, we can, for example, have a translation system. At the beginning, with the symbolic system hypothesis, the idea was to represent language as grammar with the words and the meaning of it explicitly in a symbol system. Now with deep learners, we don't deal with the symbols directly. We process the knowledge in the text with a neural network. And we can also combine this with text image recognition. So we can have an image. The system identifies the text in the image, makes a translation, and creates a new image with the translated text. Interesting application. Another application is picture coloring. So we have black and white pictures. We can also have black and white movies. And now the system is able to color the picture or the movie. But there are also applications that are more creative. For example, music composition. There are already applications that can compose music, for example, of Chopin. So very interesting applications that are kind of intelligent, based on the data that we process very fast with a system that is now able to also process huge amount of information. And this started recently because now we have the machines that can process this huge amount of information. But there are also challenges for these data-driven solutions. I have here 4 challenges: the discontinuity, explanations, limited data, and compliance. I will go through these challenges. For example, first, discontinuity. We can look at the data processing from a temporal perspective, time. So we have the timeline, and at some point of time, we collect the data. Okay, and now we learn from the data and then we can apply it. But application is based on historic data. So we collected the data and later we apply it. And this works very well if there is a continuity between the past and the future. For example, in image recognition, face recognition. The face recognition is the same whether we did it 2 years back, now, or in a few years. So the faces are similar. They're different faces, but face recognition approach can work the same. Or with text, words and so on are still the same, so we can learn it. But there could be also a discontinuity, so some kind of a break between the past and the future. And then it is difficult or maybe even impossible to apply a network that we learned with previous data also for the future. I have here one example. This is customer behavior. We can learn from previous customer behavior for the future. What are customers interested in and what kind of customer segments can we identify and so on. I use here the example of flying because there is a change in customer behavior with respect to flying. There already was a change a few years back because of the climate change. People were thinking differently whether they should fly or not. Now with the corona pandemic, it even became more different. So now there are not that many flights. We are used much more with virtual conferences. So the question is, what is the future behavior? And will it be possible to learn from the past data or for the future behavior? And I think we can have doubts for that. Another problem is dealing with change and innovation. If we have new treatments and we learn how to treat a disease, if there are new treatments, then we cannot simply transfer the old treatments to the new situations because we would not be able to apply the new treatments. This is a problem. Or even if there are new problems, I mention again the corona pandemic, there's a new problem and the question is how can we really learn from the past for this new problem? We know that it is not that easy, otherwise we would already have a vaccination for that. Another important point is a bias. We should be aware that if we learn from the past, we transfer maybe unwanted behavior also to the future. Think of the question, what makes a good CEO? Yeah, we could use data about current CEOs from the past, and then try to find out what makes a good CEO. I made a search in the internet, and these are the pictures that I found when I made the search for CEO. What makes a good CEO? The CEO typically is male. If you look at the pictures, most of the CEOs are male, only very few female. This is not what we want. And there is a lot of evidence from applications that we have data that have a bias, in particular in these gender issues, but also with races and other issues, where we do not want to transfer the past to the future. But if you simply lose the data of the past, we transfer this to the future. Okay, so this is a matter of continuity and discontinuity. Another problem that we face is explanation and understanding. We have to make decisions. Can decisions without explanation be intelligent? If we simply apply the data and get proposals for the decision, then we cannot ask, why is this decision made? It is just in the system. But this decision has consequences. There are alternatives. What are alternatives? Why do we not use an alternative? There's a matter of trust. If we cannot get an explanation, should we trust the decision? And then there's a high risk. If we go a risk, then we want to be aware what are the consequences and why is it good to take a risk. Other traceability, compliance, other issues of explanations where we would like to have an explanation for a decision. Take again this example of diagnosis. Okay, systems are very good in diagnosing diseases based on images. For example, the cancer diagnosis. And we can use the experience of many people to have a good diagnosis. And mostly we are happy with it. But now think of the next step. This is therapy. If you diagnose cancer, you have to decide for a therapy. If the system now suggests to make a surgery in my brain, I'm not sure whether I would trust it. So would you trust your decision if she cannot explain why she recommends a surgery? So these are areas where we would like to have an explanation and not just data. Explanation means rationality. Other applications of deep learning are image classification. So we can classify images according to people, or according whether it's an airplane, an automobile, bird, cat, and so on. But what about the knowledge behind it? What are the criteria? So we can detect or classify images, we can detect objects in an image, but for this the system does not have a concept like a cat, a dog, or a duck. So if we would give images of objects that are not in line with what we want to look for, the system would not recognize it. And it does not even recognize that this is a dog. It is just an element of a specific category or a specific concept without knowing it. And here's a picture that I took in the cradle of humankind in South Africa. You look at that, we have pictures of people. But now look in the center. There is a picture of a primate which is not a human. If you give the system this kind of data, it would not recognize that this is not a human. We can reason about it. We also find known about the development of humankind and what happens in which era, and so we can make a reasoning about it. This is not possible for a system if it does not have a concept of what is a human, what is a primate, and so on. Another topic, understanding and explanation, where we have deficiencies of this machine learning. And then there's the problem of limited data. We can learn if we have a lot of data, like the examples of the diseases for cancer. If we have many pictures of people with cancer, we can learn from it. What is with the diseases that are rare? If we do not have enough data, we cannot really learn of it. And there are about 7,000 rare diseases worldwide. So we don't have enough data, so we cannot really distinguish between them. Or think of products where we have special editions. Special editions means that we have only a few of that product. So we cannot use them in the recommendation if we have a recommender system, because in the past data we do not have the special edition, and if the special edition is only on the market for a few weeks, we can also not relearn it, because as soon as we learn the behavior of the people, the product is not on the market anymore. We also have the issue of compliance. Think again of the self-driving cars. What we can learn from data is the driving behavior, recognizing obstacles, braking, and so on. But there's also other knowledge that we use for driving. For example, we have the traffic rules. We have to stop at a red light, for example. These are rules and knowledge that we cannot learn. Rules have to be obeyed all the time, and if the rules change, they have to become effective from one day to the other. So there is no data from which we can learn the rules. Then we have compliance rules in other areas. What we can learn from data, for example, are risks, profits, losses. The compliance rules in different areas, they are like laws. We have to obey them. So, for example, if you ask for a credit, there are rules about giving credits, or insurance, or drug development. When it's about health issues, we have compliance rules that we have to follow. This is knowledge that we cannot learn, that has been becoming effective as soon as they have changed. And I have an example here. This is the application of health insurance application. Think of a person who is applying for a health insurance, and we want to decide whether we should accept this application or not. And there are different kinds of knowledge. On the one hand side, we can use data about clients, data about their age, former diseases, surgeries that they had, allergies, and so on. On the other hand side, we have the knowledge of the company and the compliance rules. For example, we say that only applicants from Switzerland are eligible, and that an applicant must be at least 18 years old. Or a strategic rule that says that we only accept clients which have low risk. We can combine these two data. On the one hand side, the eligibility rules that come from the knowledge, and the risk that comes from the data. And we say that only persons with low risk who are eligible are accepted, and if a person has a medium risk or if a person has a high risk, this person is rejected. So we combine, in this case, machine learning and knowledge represented as rules for this health insurance application. So the client data is used for risk assessment, and the knowledge about the compliance and strategies are used for the rational thinking. The second application that we built, this was about a whiskey recommend. The question is, which whiskey do you like? The idea came up when we were at a fair and we could talk with people about whiskies. So we have a whiskey expert whom we could ask. Now the question was, can we build such a whiskey expert also in a system? So the idea is to have a kind of a virtual bartender with whom we can talk, and the system should then recommend a whiskey that tastes for us. Now this is the first problem. How do we describe taste? There are some profiles for taste. I took this from the website of the Scotch Malt Whisky Society. A number of categories and the description. It's difficult to understand the description and to compare it to a whiskey if we taste it. And yeah, there were also some nice individual whiskies that were described, and if you look at that, then you recognize that it's nearly impossible to describe. So here are some examples. So this is a palette based on sunshine glow of tropical fruits. Oh, we can imagine that, with salt and pepper crisps, we know that. But look at this, there's something with balsamic vinegar and party nuts. How can we combine these two things? Or even more, if you think here of water-polished mahogany, how does it taste, water-polished mahogany? You see it is difficult to describe a taste. So it's much better to learn from previous behavior whether whiskey would taste us. So this is what we have, collaborative filtering, customers also bought, and so on. This is what we know. But now we have a problem. I already mentioned limited data, and we find this in the whiskey. There are limited editions. So this is a series from a distillery, from Lagavulin. They have editions every year. So there are only a limited number of bottles for that, and every year they are different. Or there are only small batches of a whiskey. Or even more difficult it becomes if we have single casks. There's a single cask which is filled up, which has about 160, 170 bottles. So we will not have data to compare this with previous whiskies because this is new and nobody has any experience in how it tastes and compare it. So what can we do? Now we can think of using the expert, because this is what we do with the bartender. We talk with the bartender or the whiskey expert. And what we did, we built, in addition to the taste that we can compare, also an expert system. So we built a knowledge base about distilleries. So Lagavulin and Ardbeg are from Islay, which is an island. Whiskies from Islay are typically smoky, and we have information about how to produce whiskey. So whiskies can be finished in different casks, and vanilla flavor comes from oak casks, and so on. So now again, we combine data-based information with knowledge. So for the recommendation, we first use the data from the collaborative filtering, and we use the knowledge of the AI experts. And again, combining them, we can build a recommendation which we also can talk about. We can recommend whiskies based on a discussion, as we would do it in a bar. Now let us come back to the different ways of thinking. We already know that we can regard human thinking as composed of two systems. On the one hand side, we have the system for the processing of huge amounts of information, and on the other hand side, we have the rational thinking. We can look at the information processing as a pre-processing step for the rational thinking. So we analyze all the sensor data, images, audio, and so on. We make a first classification, recognize what is important, and based on this, we can make decisions. We can apply this also to AI systems. Have again a look at medical application as we already did before. So we want to build an AI system for diagnosis. So this can be based on image processing. We compare an image with images that we already have in a database and we make a diagnosis. But as a next step, we have to also decide for a treatment or therapy. So we can use the diagnosis as an input for the next phase, for explanation and decision making, which is then based on medical knowledge or rational thinking. And this then leads to a treatment. So a combination of huge image processing with rational thinking. Another application could be fake news detection. So the objective is to recognize whether a news is fake or not. In the first step, we could build an AI system based on data. So we identify from the news suspicious news, those that might be fake. This can be based on a classification. This is then the input for our next phase where we go in more detail. We do the fact checking. We compare the suspicious news with facts that we have in our knowledge base by applying rational thinking. And then we can determine whether a news is fake or not. So as a summary, our approach is to combine this machine learning with knowledge bases in an AI system. So we use machine learning to deal with unknown knowledge or tacit knowledge, which we can derive from huge amounts of data. For the rational part, we use knowledge engineering. So we build a knowledge base which allows us to do the rational thinking and allows us to be compliant with rules that we have to take care of. And we can also think of a role of the human that is still available. So the human can support or be involved in this thinking if it is about innovation or flexibility to provide additional explanation. So by this we combine machine learning based on data with rational thinking by a system in a knowledge base, or maybe also involving the human.